So this work came out of Lustre 2024, the Lustre User Group 2024 meeting, and we were looking for a way to mitigate some of the file systems issues we were having on assured file systems. We were getting some batch jobs that were creating issues with denial of service, and so we worked on this over the last year to implement a lot of these new improvements based on features that were kind of obscure inside Lustre at the time. So scratch file systems are shared at Sandia between several users and lots of HPC and several HPC machines. There's lots of compute nodes running batch jobs that are interacting on these shared file systems. One bad batch run would take and give us issues with I/O loads on the MDS servers and the OSS servers. And so we wanted to reduce that impact. We wanted some control over the I/O that was going into the file system, and we wanted to be able to make it so the file systems were snappy for all the users and basically protect the file system from falling over. Lustre has token bucket filters in there that control the transactions for the remote procedure calls. And what we did was we implemented the token bucket filters to control, again, the RPC rates going into the network request scheduler. That's built into the Lustre file systems so it can respond to transaction requests, whether that be read, write, or metadata operations on the file system. And it gives us some throttling control with the token bucket filters. So we use those to modify the file system interactions so we can control things. This is kind of a big picture look of what's going on. For instance, in this case, we would have client one. Each one of these boxes represents an RPC transaction. There's a chain of them. And each client would, from whatever batch job on whatever HPC system that's interacting with either an MDT or an OST, would go through the network request scheduler to say, hey, I need this information. I need to make this file modification, whether it be metadata or storage. And that's kind of a big picture look at how that goes. I stole this picture from some documentation on the site for documentation for the Lustre file system. Again, we've got first in, first out queues. Token buckets would limit the rates, and like I said, we want it to be snappy, so we experimentally went through the whole file system to see if it's a disk loaded back end, physical disk or NVMe, what that would look like. And we figured out the rates and to get snappy, and then we did a little bit more tweaking as we ran it in real world situations, so we could, again, make sure the customers were getting the responses they wanted, but also we wanted to make sure we get control over things. This is a kind of a method that we have. You can use, we set up a base rate, and we set that base rate based on a NID. So we took a bunch of gateways. You've seen a lot of gateways that people are using. The last talk had gateways. So we set those up by NID, and then we said, okay, let's set our base rate based on experimental testing. We ended up with 1,000 tokens per second, and that was for a disk-loaded back end. And then what we do is we would have a range of gateways going at that, responding at that rate, compute nodes responding at that rate to the MDS and the OSS servers. We did find that using token bucket filters gave us a little bit of an improvement on fallover just by implementing them. We did again, a lot of testing, and experiments, and we found out that, hey, it allows us to keep our file system up a little longer too if we have issues with people hammering the file system. We used an in-house program that somebody had written that we knew was going to make the file system fall over because he made the file system fall over pretty consistently. One thing that we did find out was even though we had a token bucket filter rate of 1,000, if somebody had a whole bunch of gateways they were running through, we could still knock over the file system if they were still going to the same stripe. So the way the setup was done in Lustre, we can actually stack the transactions. So if somebody by user ID, job ID, and the base rate, which we set by NIDs on the gateways. And what we did was we set the rates at 1,000, and then we would, if somebody was still hammering the file system, if they had a bad job, they were running out of a bunch of gateways, we just layer on top the user ID or the job ID, and then we could limit that person for until we got a hold of them and said, hey, your job's running, this batch job's running poorly, we had to throttle you further. The other clients still are running at 1,000, but that one bad client, we'd limit them to like 50 tokens. So even if he was running 500 gateways, he'd still, and 500 nodes or whatnot, he would still be throttled to 50, even though the base rate for everybody else was 1,000. So they still have responsive performance, and that one person we would get a hold of them and say, hey, we had to stop your job and get control of the situation so we don't have a file system fall over. And it worked pretty good. Again, the throttled setup we can do by job ID or by NID as well. And then we would do, again, the bad client would be set up with a very low rate, and then everybody else would have the normal rate. So everything's working hunky-dory for the file system. And then in another case, Joe, for instance, asked, hey, what if we want to prioritize somebody? We can do just the opposite. We can, instead of throttling the person, we can bring them up a little bit we can prioritize them by increasing the token bucket rate for that one person. Again, it's layered on. So everybody else is getting 1,000. This might be getting 1,500 on this user ID, for instance, or job ID. So we wrote a lot of code to front all this. The base controls are not that complicated. Again, everything's built into the file system, but what I wanted to do was make it so that we could easily control those rates. So I put in a layer of middleware, and then I put somebody that wasn't an expert in the file system could say, oh, I identified a bad user, I want to throttle that user, and then he would make a call to the middleware and through a front end, and then make a change to that person. We could also, if we have a file system full restart or something, the initial rates don't come in until you initialize them. So I wrote some software that would initialize the whole file system by name, like the file system name. It would go through, set all the MDS servers and the OSS servers automatically, and then everything's got a base rate into it. And then, of course, we can release the bad user. Let's say we got a hold of them and said, hey, your batch job, we killed your job, or we're ready to work with you to get this thing done. We release it so he doesn't stay throttled. The bad user identification. So right now, Lustre doesn't have, these are improvements that are going to be coming, hopefully. We're going to be able to identify the bad user more easily. We want to be able to do this stuff automatically, so we don't have people having to interact with the file system. It'd be better if the file system was able to make the changes itself. So what we do is we identify the bad user with, by putting in the information that's already in the front end of the network request scheduler. We poured it through all the way through the to the back, to some ports that we would pull in the network request scheduler and say, hey, who's this job ID running? Who's the user ID number running for this, this job that's not working well? And we can use those to gather the IP address of the bad job, identify the cluster it's coming from basically, and the job that's running on the bad cluster. And using that information, we can use that information in a lot of ways. Like I said, we can automate the file system to protect itself without us having to interact with it. So it's a Christmas day and 12 o'clock midnight or something, we don't have to be there to make sure the file system doesn't fall over. We don't have to get a hold of the user or some. In that case, it would do it itself. And then a little further along, what we can do is we can automate the things so that we throttle the bad batch job until that bad batch job is done. And then we can bring that bad batch job, we can throttle that bad batch job and the rest of the user ID. Let's say he's a big user, we can make sure that he has full throughput on the rest of his batch jobs. So we're just selectively doing that for the time period that that bad batch job's running. So there's a lot of advantages with the putting the information through all the way through in the network request scheduler. So again, we're missing that information right now. It's in the network request scheduler at the front end. So we're just going to add that information in to the network request scheduler so we have the full association all the way through and we can pull that information. Another thing that I'd like to do is right now we're doing first in, first out. If you do want to pick round robin, you can't do the token bucket filters. I'd like to make it so that we can do both. Because the person that's doing the first in, first out gets the lock on the file system, OST, or the MDT until they're done with it. So if that person's doing a set of transactions, the client behind it has to sit there and wait until he's done with his RPC transactions. What I'd like to do is use round robin. There's something in the network request scheduler called client round robin. It would be nice if we could do both, because then we can stack, one client gets a little bit of a time slice, then another client gets another time slice, and what that does is everybody gets some response, even if somebody's bogging down the RPC transactions with a large transmit or whatever. They each get their own quantum. And so I'd like to make some special things. I spent a lot of time. Chuck Ritter from DDN originally got me onto the token bucket filters. It's kind of not always fleshed out at the time. And then, of course, I got a lot of help from Andrea Stilger and James Simmons. And then, of course, Jill Mervini assigned me with the task of implementing it. So does anybody have any questions?
Hi. When you're looking for pathologically bad workloads, are these just overwhelming your systems from a resource perspective, so you can only do so many metadata IOPS, or you can only do so much storage, or is it?
Yeah, so what happens is if somebody is trying to access your file system, they're going to at some point overload the file system. It'll start thrashing the MDT or the OST, and so you'll be basically taking the file system down if you're not careful. And what we did was we wanted control over that. We didn't want unlimited I/O transactions. We wanted it to be responsive, and we wanted everybody else to know they could count on the file system to be up.
Okay.
And again, there's a fine line of responsiveness. We want people's batch jobs to run all the way through without them taking 3 days. to run where they took one day before or whatever. But the other side of the stick, we wanted to make sure that file system didn't fall over, so people had to resubmit batch jobs.
Gotcha. I mean, the only reason I asked is because we've looked at something like this before at our site, and our conclusion was that all the things that we normally see that could cause a file system problems, whether this be Lustre or NFS or something like that, normally it's like some pathologically bad workload that like doesn't show up as like too many RPCs, but it's just someone doing something really dumb on the file system. So like, you're not seeing, 100 gigabytes per second, you're seeing 3,000 set adders in a loop, just something completely crazy where an RPC throttling wouldn't kind of show this.
Oh yeah, so you can see the load go up on right before they start, the OSTs and the MDTs start, OSS servers and the MDS servers start to fall over. You'll see the load go up, and that's a response to the RPC transactions. So if somebody's writing 3,000 nodes to one stripe, you're going to see something weird like that. So
I feel like that falls into you should fix the code.
Yeah, well, yeah, but you can't know who's going to do it ahead of time. So
I have a question. So you said the RPC can overload the OST because of some host drive, right? So did you consider like I see all the talk is about like throttle from the client side. Do you consider like throttle from the server side, OST server side, something like that?
we don't generally throttle it from the client side. It's being done at the server with the token bucket filters. That's a nice thing is that you don't have to throttle it. You don't have to go through and preset stuff on the clients. You can let them run through. And then if you want to make tweaks, you make it at the server side.
Okay.
I had a question, Michael. Can you talk? Did you have any process by which you established like the rates that you were using, like to come up with? Like,
Yeah, we did that experimentally, and then once we had it kind of in the range what we thought it would be, we put it out in production. But then there were still some tweaks that we had to make, and that was done over maybe a month after we implemented it to fine-tune things.
Yeah, so you would sort of look at the result and
yeah,
and tune up
if
and
somebody's
down.
running an LS and it takes them 5 minutes to run an LS on a directory, then hey, we need to relax the load. But if somebody's knocking over the file system yet, then we would say, oh, okay, we need to be down a little bit. So it was done a lot, like I said, experimentally, but then at the end it was fine-tuned just to
do you still interact with it, or is it you've kind of reached the rate now that you're pretty happy with, and you?
Yeah, I think we're in that fine sweet spot. So.
Okay. Thanks, Mike.